Hi class, in this video I want to go through questions 2 to question 10 from exercise 6.10, the rates of change. Question 1, I'm skipping over that because it's mainly differentiating different types of functions. Hopefully you can get those. Please send me a message if any of them you need help with any, but here's pretty much the solutions for question 2 through to question 10. So we'll start off with question 2, h equals t cubed minus 7t plus 5. We want to find the average rate of change for part A. So the way we go about doing that, we're going to work out the value of h at 4 and 3. So we're sort of going to work out the value of h at 4, value of h at 3, and take that away from the time at 4 and the time at 3, which is just going to be 4 take away 3 here in the denominator. So the value of h when t equals 4 is going to be 4 cubed minus 7 lots of 4 plus 5, and that gives us a value of 41 when you evaluate it. h3, just substitute 3 in, and when we evaluate that we get 11. So therefore the average rate of change would be 41 minus 11 all over 4 minus 3, 30. We're going to get that at the top, so our rate of change for this function is 30. We've got no units here, so the answer there will just be 30. Part B, what's the instantaneous rate of change? Well, to get the instantaneous rate of change, we can use differentiation. So dh dt, that will give us the instantaneous rate of change. That'll be 3t squared minus 7. We want to know the value when t equals 3, so we just substitute 3 into there, and so we'd get 3 lots of 3 squared, so it's 9 times 3 is 27, take away 7, and that should give us a value of 20. Interestingly enough, question 1 we had to work out the average between 3 and 4, and we got a value of 30. We worked out the exact rate of change at 3, and it was 20. If we go ahead and substitute 4 into this equation, we come up with an answer of 41. And if you have a look at those, the average of those two quantities is very close to 30. On to question 3. The volume of water in litres that flows through a pipe with t in seconds is given by V equals t squared plus 3t. Find the rate at which the water is flowing. So that's a nice easy one for us. The rate is dv dt, so the first derivative will be 2t plus 3, and substituting t equals 5 into that equation, 2 5s are 10 plus 3, and that'll give us 13. For this one we do have units, so we've got litres and seconds, so that'll be litres per second. An alternate way of writing that, which we looked at in the tutorial video I did earlier today, 13 litres per second, and we can do the per second with a little -1 next to the s. On to question 4, the mass in grams of a melting block of ice is given by m for the mass equals t minus 2t squared plus 100. We want to find the average rate of change of the block while it's melting. There's 2 times we're going to do here. I'll just do the first one, leave the second one up to you. So we're between 1 and 3, so we want to kind of know what's m3 minus m1 all over t3 minus t1, where this is just 3 and 1. So the mass after 3 minutes, we'll substitute 3 into this function up here. We'll get 3 minus 2 lots of 3 squared plus 100, and that gives us a mass of 85 grams. And the mass after 1 minute, substituting 1 in, would be equivalent to 99 grams. So the mass after 3 minutes is less than it was after 1, which makes sense because it says here in the question that this ice is melting. So the average rate of change will be 85 minus 99 all over 3 minus 1, and that gives us a value of -7, and the units there will be grams, which I'll just use as a G, grams per minute. So we'll just write grams with the minute and the -1. Part B, find the rate of change of melting, and so this is another way of saying the instantaneous rate of change. So we're going to use the first derivative, so dm dt. The t, the first term in the equation up here will become 1. The derivative of 2t squared will be 4t, and the constant term 100 will disappear. So the first derivative is 1 take away 4t, and at t equals 5, we would get minus 19, and that will be 19 grams per minute, which kind of makes sense that the rate of change is slowing down because the mass would be getting smaller and smaller as we go along. On to question 5. The surface area of a balloon is given by this function t cubed minus 2t squared plus 5t plus 2. T is in seconds and the area is in centimetres squared. Find the rate of increase at 8 seconds. So we want to find ds dt. That will be 3t squared minus 4t plus 5. That's our first derivative. The value of that after 8, substituting 8 into that equation, plus 5, and if you use your calculator for that one there, that comes out to be 165 centimetres squared, so it's a unit of area, per second. On to question 6. A circular disc is expanding when it's heated, so it's potentially made out of metal. The area in centimetres squared of the disc increases according to this function, A equals 4t squared plus t. Find the rate of increase of the area after 5 minutes. So we're going to get the rate by getting the derivative, and that'll be 8t plus 1. So the t, remember, will just become a constant 1. Substituting 5 into there, 8 lots of 5 is 40, plus 1 gives us 41, and our units here will be centimetres squared per minute. So we can write that like that, or you could just as easily write it like that. The key thing is the value of 41, which you get from the derivative. Question 7, a car is d kilometres from home after t hours. So our units are kilometres per hour, I guess, if we're talking about speed. And we've got the formula for the displacement, 10t squared plus 5t plus 11. Now, interestingly enough, the term displacement means the distance from the origin that the particle would be. In this case, the particle is a car, and the origin is home, and that would be counted as d equals 0. And so this function is going to tell us by substituting t in how far away we get from this origin. So question A, how far is the car initially? So that will be t equals 0 after 3 hours and after 5 hours. So we're just substituting those values into the equation. So t equals 0. We're going to get 10 lots of 0 squared, which is 0, plus 5 lots of 0, which is 0, plus 11. Initially, the constant term in any equation is always the value that we'll end up with. So in this case, at time equals 0, this car is 11 kilometres from home. Part 2, after 3 hours, the distance will be 10 lots of 3 squared plus 5 lots of 3 plus 11, and if you do those sums, you get a value of 116 kilometres from home. And part 3, the distance after 5 hours, 10 times 5 squared plus 5 lots of 5 plus 11 gives us a value of 286 kilometres from home. If we have a look at part B, what speed is the car travelling at after 3 hours and after 5 hours? Well, that sort of coincides with those distances. First of all, to get the speed, remember the velocity speed is equal to the derivative of the displacement with respect to x. In this case, we're using d for displacement, so we get this funny looking dd dt. Nonetheless, we'll differentiate that. We should get 20t plus 5 as our velocity equation, and substituting now, so for part 1, when t equals 3, we're going to get a velocity of 20 lots of 3 plus 5, so this car's travelling at 65 kilometres per hour. After 5 hours, the velocity 20 lots of 5 plus 5. This car is now travelling at 105 kilometres an hour. So the car's accelerating, and it's not part of this question, but if we were to work that out, acceleration is the derivative of velocity, and if we get the first derivative of this equation, this car is travelling or accelerating at 20 kilometres per hour every hour, just meaning it's getting 20 kilometres an hour faster every hour. And you can see here, after 2 hours later, it's 40 kilometres an hour quicker. On to question 8. According to Boyle's law, so doing a little bit of chemistry here, the pressure of gas is given by P equals K over V. V is, or K is a constant, and V is the volume. It says here, if K is equal to 100 for a certain gas, find the rate of change of the pressure when the volume is 20. So if we substitute, we've got this equation. If we firstly substitute V in here, now we want to know what is dP dV. We have a fraction here, and you might remember last week we might use the quotient rule for anything we have to get the derivative of that looks like a fraction. But let's make life a little bit simpler for us by putting this in index notation. We've got a v to the power of 1 down the bottom of a fraction, so we could go ahead and write this expression as 100 times v to the minus 1, getting rid of that fraction. So now if we get the derivative of this function, here's the power. The power, remember, multiplies by any coefficient, and we just take 1 away. So we're going to get minus 1 times 100, just minus 100, v, and we'll subtract 1 from that, will give us v to the power of minus 2, which we could then rewrite back in fractional form as minus 100 over v squared. We want to know the value of this rate of change when v is equal to 20. So if we substitute v equals 20 in there, minus 100 over 20 squared. Now 20 squared is 400, so we're going to get minus 100 over 400, which is minus a quarter, or in decimal form, minus 0.25. There's no units given here, but generally gas could be given as like in kilopascals for pressure, and volume potentially could be millimeters, probably centimeters cubed. On to question 9. The displacement of a particle is equal to t cubed minus 9t. We want to find the velocity, we want to find the acceleration, we want to show that the particle was initially at the origin and find any other times when it was at the origin. It's an interesting question. And at what time will the acceleration be equal to 30? One of the cool parts about using calculus now in your maths is if you have an equation that models a system, you can determine its speed and acceleration and its distance from the origin at any time in the future. So for part A, find the velocity. Well, the first thing we have to do is work out the velocity equation. So we're going to get the first derivative of displacement. In this case, that will be 3t squared minus 9. Find the velocity after 3 seconds, so we'll just substitute 3 into that equation, and we'll get 3 lots of 3 squared, which is 27 minus 9, and that gives us a value of 18, and our units are centimetres and seconds, so that'll be 18 centimetres per second. Part B, find the acceleration at 2 seconds. So acceleration is the first derivative of velocity, and the first derivative here will give us 6t. That's our acceleration equation. It's a variable because there's something to substitute changes with time. Substituting 2 in there will give us 6 times 2, and so that'll be 12 centimetres per second per second. So it's increasing in speed by 12 centimetres per second every second. So that's why for acceleration we put a minus 2 here. Part C. Show that the particle is initially at the origin. So initially, the word initially in any question, remember, means t equals 0. So we could go ahead and do it the simple way and write, well, it's 0 cubed minus 9 lots of 0, and obviously the displacement is 0, which, x equals 0 is the origin. But there's a better way to do this, and it would coincide with find any other times that the particle is at the origin. and I'm just going to take a new page for this section. So rewrite the equation x equals t cubed minus 9t. Now we should look to find any time where this is equal to 0, just like we would for a quadratic equation. Always see if you can factorize it. It could make life so much easier for you. Now here we've got t in both of these terms, so let's see what happens if we take t out as a factor. That'll leave us with t squared minus 9. Now the t squared minus 9 binomial, we can factor that even further, and that'll give us t minus 3, t plus 3, difference of 2 squares. And we want to know when that's at the origin, so when does x equal 0? So pretty much solve this equation, and I hope you can see, well, that'll be true when t equals 0 and when t equals plus or minus 3. Now if we were to sketch that curve, ooh, excuse my wonky axes there, that will give us a solution at minus 3, it'll give us a solution at 0, and it will give us a solution at 3. And if you sketch that curve, the original displacement curve, would look something like that. This equation here, if we graphed it, would look like that. Now a key thing which we'll go on to in year 12 is that any questions to do with displacement, velocity and time cannot be negative. Everything starts from t equals 0. So even though mathematically minus 3 is a solution, we're only interested in solutions from t equals 0 and beyond. So t always has to be greater than or equal to 0. So to answer that question, if we go back, find any other times that the particle will be at the origin, mathematically minus 3 is a solution, but this correct solution will be 0 seconds and 3 seconds. So really 3 seconds is the other time. And part D, at what time will the acceleration be equal to 30 centimeters per second? So we've got our acceleration equation here, 6t, or a equals 6t. So we're really just solving when does that equal 30. Nice easy one, and that would be t equals 5 seconds. On to the last question, question 10. A particle is moving with a displacement. This time we're using s as the pronumeral for displacement, and we've got meters per second. We want to firstly find the initial velocity. Well, firstly we need to go get that velocity, ds dt, and that'll be 4t minus 8, and initially t will be equal to 0, so 4 lots of 0 minus 8, so that will be minus 8 meters per second. So what that means, just to interpret that really quickly, a negative velocity means that this particle initially is moving back towards the origin. Any positive velocities mean particles generally, if it's in the positive region, will be moving away from the origin. But this one here, this will be moving, have a negative gradient if we were to graph this function here. Part B, show that its acceleration is constant and find its value. That's pretty easy to do. A is equal to dv dt, and the derivative of this function here would simply be 4. Show that it's a constant, well, we've done that, and find its value. And if we wanted to, we probably should be writing that as meters per second, or meters per second to the power of minus 2. C, find the displacement after 5 seconds. So we're substituting 5 into that original equation that we had. And that gives us a value of 13 meters. Part D, find when the particle's velocity is 0. So for that, we're just looking at the velocity equation, which is here. And we're solving when does that equal 0. So it's just a nice easy two-step equation. 4t equals 8. Therefore t equals 2, so at 2 seconds the velocity of this particle will be 0. Our last question of the set, what will be the particle's displacement at that time? So at 2 seconds, and I'll do it up here for part E. 2 squared minus 8 lots of 2 plus 3, and if you chuck that into your trusty Casio, we get an answer of minus 5 meters. What does that mean? Well, this is 5 meters on the other side of the origin from the positive side. So if you were graphing x up here, so it's distance from the origin, and this would be time, its displacement after 2 seconds would be somewhere down here. Now, if you were to graph this function might look something like this here. Be a parabola. Obviously, it's going to have a positive 3 as its y-intercept. Its vertex, if we try to find what x value would be here, well, remember the vertex is at minus b over 2a, which would be at 8 over 2 lots of 2, which would be 4. So that would be at x equals 2. We know it's a positive concave up parabola, so it has to be below the axis here. And so what's actually happening here, the displacement at 2 seconds is minus 5. So it's just saying that this value over here, it's 5 units. Generally, they count positive displacements as the right-hand side and negative displacements as being on the left-hand side of the origin. I hope all those questions made a lot of sense. If anything didn't, just send me an email and I can go back over any of those questions for you. Take care.